That's right. Okay, so this mic is also working. That's good. Yeah, so Johannes emphasized mathematics. That's because I'm a mathematician. So I'm going to warn you now. You can ask me about the physics, but chances are I will not be able to answer, and I'll refer you to some local experts like Shruti or Johannes, as some other people in the audience. So yeah, I would, however, like you to ask me all questions you have about the mathematics. I've tried to kind of remove as much jargon as possible, but probably I don't even know what some of the jargon is. So yeah, if anything seems unclear, please speak up. I would ask that you use a mic when you ask a question if possible, just because I think on Zoom they can only hear you if you use a mic. So it's just a little nicer. Okay, so the place that we'll start is some physics motivation. And then we're going to kind of take a detour into some mathematics sitting in the background, and then eventually we'll get to the Amplituhedron. Okay, but the physics motivation is a method for computing scattering amplitudes that Johannes mentioned in passing. So we've talked a lot about Feynman diagrams so far, but there's another method of computing scattering amplitudes in n equals 4 super Yang-Mills, which is recursive. And it's called the Brito-Cacciazzo, Fang, and Witten recursion. So their paper, I think, is around like 2005. So this is like maybe not such an old method. Yeah, so this is a recursion for n equals 4 super Yang-Mills amplitudes. And I'll say I'm only going to be talking about tree level. And I think, in fact, their original paper is only about tree level, but then it was generalized to all loop by, a paper which includes, for sure, Nima, Arkani-Hamed, Trnka, and then more authors, which I'm very sorry I've forgotten. That was around 2010. Okay, so what is this recursion? Well, pictorially, it looks like this. So we're talking about an n-point amplitude. The k tells you about which helicity sector you're in. Okay, and the way you should interpret this is each picture here represents a function, a rational function, in particular a Yangian invariant. Okay, and it's recursive. So what do? You sort of take the pictures that you got for n-1 points and the same k, and you sort of stick them in to here, right? So your G prime is ranging over all the pictures you got for a lower point amplitude, and you kind of stick them in here, and then you decorate with a little extra bit. Okay, so that's one part of the recursion. And then another part of the recursion is sort of a product. So there's some range over this index J, and then you're going to take all of the pictures you get from sort of a left amplitude, so some smaller number of points NL and some smaller helicity KL, and you sort of take all those pictures and stick them into the left part of this picture, and then you similarly have a right part and you stick all those pictures you got from your lower amplitude into here. So in reality, right, this is recursive, so I would start with this, and then I would say, okay, now I'm going to use the same method to compute this amplitude and the same method to compute this one, and it just kind of keeps going all the way down. Okay, so yeah, it's recursive, which is not the most straightforward thing to think about, but it is a method. And you'll have to talk to someone else about how it compares to the Feynman diagram computation. Okay, so I want to say two more things about this. The first is that this phrasing, in terms of exactly these diagrams, is in momentum twisters. Which are sort of these magical coordinates that Johannes mentioned briefly, which make Yangian invariants kind of manifest. I'm not going to tell you yet what momentum twisters are, but you should just think this is the recursion phrase in some very good kinds of coordinates. Okay, and then the other thing I'll say is that in this equation, I had a choice at the beginning, like when I wrote down this equality, I had a choice which was I get to choose this index I, this special index I here. So to write down this equality, I choose an I. And that means that I have lots of different equations that I can write down, right? Because I have n different choices of I, and each one will give me something that looks like this, but then as I recurse down, I keep having choices for which I pick. And so this recursion produces many, many, many formulas, different formulas for the amplitude. And I guess that's a big difference from the Feynman diagram picture where really you just have kind of this one distinguished formula. Okay, so let me write down some of this stuff I just said out loud. So, right, so what did I say? I said, so each graph here, you should think of as representing a rational function, and in fact a Yangian invariant. Right, and then the other thing I said out loud is that the sums are over graphs appearing for a smaller n and k. And right, the other thing I said is many, many formulas, or this method gives you many, many formulas, which I'll call sort of just BCFW formulas. For your single amplitude. Okay, and oh, the other thing I should say is that these graphs, these pictures that I'm drawing, right, they're not Feynman diagrams. They're sometimes called on-shell diagrams, or mathematicians like to call them Plabic graphs, which stands for planar bicolored, right? So all my graphs are planar, and they have these two different kinds of vertices, hollow and solid. Okay, so yeah, so this is the graphs themselves are called on-shell diagrams, or Plabic graphs. I didn't explain it at all. Yeah, and so I will not explain it again at all still. Yeah, so physicists will tell you something about what they mean in the on-shell diagram context. They'll mean something else later, sort of geometrically combinatorially, which I'll talk about in a second. Yeah. Okay, so before I kind of, so this, the many, many formulas for the amplitude is sort of what we're going to hone in on, and it's going to motivate everything else. But before I do that, let me just tell you, like I gave you a recursion, and so maybe I should tell you what the bottom of this recursion is. So, right, so then when you get to the end, you know what to do. So here are some examples of what you get if you run this recursion. So if you try to take, yeah, so this is maybe a formal thing. If you take the endpoint amplitude and your k is 0, then I'm just going to declare this. This is what you get at the bottom of the recursion. You get a graph which just has these solid lollipops, and there are n of them. Okay, so that's the bottom of my recursion, is such a graph. Yeah.
Sorry, is k equals 2 MHV or k equals 0 for you?
I think k equals 2.
K equals 2, okay.
Yeah.
Thanks. MHV.
I actually can't remember. Oh, that might have been really wrong. I don't know. I can't quite remember. Dimitri, what do you say? Okay, this is MHV. Okay, thank you, Dimitri. Okay, okay, so let's do just one step in this. Okay, so this is AN0, and then maybe the next one to talk about is A51. And it turns out when you run this, the only thing that shows up is something from, yeah, so I haven't told you all the details here, but the only thing that shows up should come from this kind of term. Oh, the other thing that I forgot to tell you is this, the helicity for the left and right, they need to add to the overall helicity minus 1. Okay, so here I've got k is equal to 1. So in this picture, the left and the right k have to add to 0. And so that means that both of them in fact are 0. And so the only kinds of things I can stick in for these blobs are this kind of picture. Okay, so yeah, so for some choice of I, maybe I choose I is equal to 5. the picture I get is this core here, this kind of butterfly. Sorry, slow. Okay, and the only thing that I'm allowed to have in this butterfly basically are these lollipops. Okay, and I said I was equal to 5, so that means this is 5 down here. So I just get this single graph here. And I'm not going to tell you why, but there's some moves you're allowed to perform on this graph. And in particular, you're allowed to kind of suck in all of these black lollipops. So those can all be absorbed. And then you're allowed to delete degree 2 vertices. So I'm just going to say there's some transformation you do. And what you get in the end is something that looks like this. Okay, so that's one step of running this recursion. And maybe I'll spare you. I had a more complicated thing that you get after running it more times, but maybe I'll be kind of slow to do it. So maybe I'll spare you watching me do a big thing. Yes? What are the building blocks? How am I supposed to build something like this? So it's recursive, right? So no, without knowing the recursion. So I think if I just look at the first one, which is image, right? It has to be some basic building blocks to start with. Yeah. So the idea here is that what's happening is so let's see, what's the right way to say this? So I think what's going on is basically like the idea behind the BCFW recursion, one of the ideas behind it is you should view a higher, like this endpoint amplitude, as you can kind of degenerate it to your smaller amplitudes by shifting some columns of a matrix, basically. And so what's happening here is this diagram in the middle is dictating exactly how that shift is happening. And then you see your smaller, like whatever you got in the smaller amplitude sitting inside. So it's recursive. You start from the top down. So the idea is not to build up from the bottom, but instead to think I have this large complicated amplitude, and if I do some shifts, I'm going to get a smaller amplitude, or kind of some complicated product of smaller amplitudes, and that's what this diagram is encoding. Yeah. Seem okay? No, but BCFW falls down to just 3 points, right? And then you start doing them together to build pairpoint amplitudes. It does have a building block, right? So this is in momentum twisters, which is maybe not the way that you've seen BCFW phrased before, and it's a little trickier in that context. Yeah, so maybe I should say there's another picture for BCFW, which looks like this. This one is not in momentum twisters. It's sort of in the more obvious coordinates. And what I'm going to say is I think what you're thinking is maybe a little bit easier to see in this picture, and in this picture you really need to think about these shifts, these degenerations to smaller amplitudes. Okay. So, any other questions? Mm-hmm. Broken up the 4 into 3. Mm-hmm. I'm not seeing that either in this picture or this picture. So that's how one would have thought of BCFW. Please explain how that would fall into this. So yeah, again, I'm going to say this falls into this. So actually, can a physicist remind me of which coordinates we use for the spinor helicity? So that would definitely fall under this category. What's happening here is, okay, so maybe I can say this corresponds to some kind of like soft factor over here, and this is everything else. I'm a bit worried that this is falling into I am not familiar enough with the physics to give you a satisfactory answer. I'm going to present this to you as, I promise, it's a reformulation of BCFW in terms of momentum twisters, and then proceed from there. Yeah. Yes. Oh, thank you. Yeah. So this is n equals 3 because inside of this blob I have sort of 3 boundary legs, and then this is 4 point because inside of here I have 4 point. Yes, that's right. So that's this picture, and it is because you're using different coordinates. Oh, this is just like you can have as many up here. Oh no, this is still like you can have as many, yeah, maybe I should put dot, dot, dot. The boundary legs are like not too important. It's like you can have like, yeah, the number of boundary legs here could vary. So is that more satisfying? I think you could have, in fact, no boundary legs and do a reduction. Yeah, that's right. Yeah, please. Okay. Do we feel satisfied with it? Thank you very much to the physicists who actually know what's going on physically for explaining. We feel okay to move on? Okay, so, right. Point of this is many different formulas for a single amplitude. I did not show you, but you might imagine as you choose these different i's, really the graphs that you get, and so also the rational functions you get are very different. So you get sums, you get expressions for the single amplitude, very different, many of them. And the question that really motivated the Amplituhedron is why are there so many formulas? So why so many formulas? An explanation for why they're equal. So they sort of have to be equal because they're all computing the same thing. But if someone doesn't tell you this in advance, then you think, oh my God, like why should these things ever be the same? And then another thing that's happening here, so we're writing our amplitude as a sum of a bunch of rational functions. Those rational functions have very complicated denominators, right? So you get sort of all of these spurious poles from this expression, and you want to understand why do those spurious poles cancel in the final amplitude. Okay. And all right, so kind of the first step towards understanding or kind of trying to answer this question is a paper of Hodges from 2009. And I think Johannes also mentioned this briefly in his lectures. And I'm going to just summarize, in my perspective, what he said. So in this paper, Hodges says we can understand k equals 1 BCFW by looking at a polytope. Okay, and sort of the schematic is we have our amplitude that we're interested in. And I'm going to write it in a funny way, right? So this is just sort of a schematic to help you understand. So I'm going to think of my amplitude as being like the volume of something, like this square. So in reality, it's higher dimensional, fine. So it's my amplitude is the volume of this polytope. And what I can do is I can compute this volume. Okay, right. So in general, it's actually very hard to compute the volume of a polytope. And what you do to compute it is you break it up into little pieces whose volumes you understand, right? And then you just kind of take the sum. So I can compute this volume by computing the volume of this triangle and then adding the volume of that, whoops, not that one. Volume of this triangle. And of course, I have a lot of different choices here, right? And how to cut my polytope down into triangles or simplices. So I could also compute the volume this way. All right, and Hodges' insight was basically all of these different k equals 1 BCFW formulas actually come, okay, so I think he was actually looking maybe in particular at n equals 6, but these formulas actually come from kind of considering some big object, a polytope, and then just slicing it up in different convenient ways and kind of computing something for each piece and then summing them together. Yeah, so I should say a little bit more. So he didn't really use the volume, but it's kind of okay to think about what's happening as a volume computation. instead, he sort of used, so instead of the volume, what's really being computed is some top degree differential form, which I'm going to call omega. Okay, yeah, again, still just a schematic. And what do we say, what's happening with this omega? Okay, so it's a top degree form, and it has logarithmic singularities on the boundary components of my polytope, right? So I've got a logarithmic singularity along this line, this line, this line, and this line, and similarly for the triangles. And the reason that we like this is because, right, I should also kind of orient things properly. The reason that we like this is it sort of explains, right, so here in this picture I have some spurious singularities, right? So I've got logarithmic singularities along this diagonal in this picture and also along the same diagonal in this picture. But because I've done things sort of carefully, when I add these two things together, kind of because I'm gluing the two triangles along their shared boundary, that spurious singularity is going to disappear. Yeah, so what I'll say is that the spurious poles disappear because they correspond to a boundary where we're gluing the pieces together. Yeah, so it's sort of, it's a boundary of the piece, but not really a boundary of our big object that's actually telling us about the amplitude. Okay, so it's important that this sort of thing makes sense because this is exactly what motivates the Amplituhedron. This is sort of exactly the sort of thing that we're looking for in defining the Amplituhedron. So if you have any questions about this stuff, definitely ask me now. Yeah. Yes.
Just intuitively, why should that be?
Well, I guess, I don't know if I have a great answer for this besides you do actually kind of want it to behave somewhat like a volume. And well, volume cares about something that's full dimensional, right? So you kind of want something that's top degree. I don't know if there's any better physics answer for why it should be a top degree form. Yeah. Yeah, okay. Okay, so this kind of understanding of the k equals 1 BCFW formulas leads us to a problem this problem that I'm proposing, its answer will be an answer to those questions we were asking over there. So the problem is to find, for general K, a geometric object which decomposes into pieces kind of according to the BCFW recursion, right? According to these BCFW formulas. And what we want is we want it to have this top degree form, right? So I'm going to call that the canonical form, which actually gives you the scattering amplitude. Okay, and okay, I know the scattering amplitude here is a rational function, not a differential form, but what you do is you write it with like the standard form next to it, and then you have a rational function there, and that's the thing that should give you the scattering amplitude. Okay, so this is the problem we want to solve. And I should say that kind of this idea is really also what is behind the definition of positive geometries, which I think someone at some point will give a more official definition of. Yeah, but this is the idea behind the Amplituhedron, and then you can generalize that to say it's the idea behind positive geometries. Okay, right, so I already gave it away. this problem has been answered. So the answer to this problem, which was by Arkani-Hamed and Trnka, is the Amplituhedron. A, N, K, M, Z. Okay, and actually I should make this a 4. Okay, and their work really, but to understand, like this Amplituhedron didn't come out of nowhere. I mean, they were really aiming for this, to generalize Hodge's observations. But their work also comes from another source, which is that these on-shell diagrams had already appeared in the math literature, in particular in work of Postnikov. And so their definition of the Amplituhedron really builds quite a lot on the work of Postnikov. On the totally non-negative Grassmannian, which I'll define in a second. And the point, like the reason why they were sort of the starting place was this space is because this space, the totally non-negative Grassmannian, already associates a geometric object to each one of those graphs. So it seems like a good starting point, right? Like we have these BCFW recursions, these formulas written in terms of graphs. We want a geometric object that's sort of related to those graphs, and in the math literature, one already exists. It's not quite the right thing. That's why we don't talk about, you do talk about the Amplituhedron, but this is the place to start. Okay, so, yeah.
Can I ask, come back about this question of this upgrade from the amplitude to the top form?
Yeah.
I'm just wondering about the choice of variables, or in other words, is it clear that that this, I mean, how to know what form to what measure to strip off? Is it just clear, or is it clear that that's independent on the changes in variables?
Yeah. So as far as I know, it's not totally clear. Yeah, I think. Yeah. So what I'll say, yeah, maybe what I should say is this. So far, the focus of mathematicians has sort of been on the first part of this sentence before the with canonical form equal to the scattering amplitude. So what I would say is like, yeah, I don't have anything actually really precise to say about this statement and yeah, exactly which thing we should strip off and exactly which coordinates we should use. I will say that probably the physics literature already makes a prediction for this, and my expectation is that that prediction is correct. But yeah, I can't say anything more detailed, I'm sorry. Okay, it's a very good question. Okay, so now having spent about half an hour telling you all about, or kind of some people in the audience actually telling me about the BCFW recursion. Well, anyway, I've given you some graphs and talked about the Amplituhedron. It's kind of a bait and switch. Now I'm gonna spend some time talking about this totally non-negative Grassmannian, which at the outset has absolutely nothing to do with amplitudes. And then once we see what that's about, then I'll tell you, okay, like it's not quite the right space, we'll do something to it, and we'll get down to this Amplituhedron, which does know about amplitudes. Okay, so. Yeah, so Z is some parameter matrix. Yeah, and then N and K are the same, and then this 4 here is because space-time is 4-dimensional. Okay, but yeah, so for now, I'm not really gonna talk about the Amplituhedron at all. I'll just talk about the totally non-negative Grassmannian. Okay, so first, just the Grassmannian. Right, so this is named after a mathematician, Grassmann. So for the Grassmannian, you fix 2 parameters, N and K. All right, we've already been fixing those. And the Grassmannian, which I denote by GRKN, is just the set of all subspaces in R to the n with dimension k. Okay? And this is all well and good, right? Okay, so I know what a subspace is, right? I know how to compute its dimension, but if I really want to get my hands dirty with this, the way I want to think about it is as the set of all full rank k by n matrices modulo row operations. Right, so I'm just thinking about some matrix whose row span is the subspace. Right, so maybe I'll take the subspace, which is the row span of this matrix. Okay, and this is some point in the Grassmannian of two planes in R to the 6. Okay, so as soon as someone hands me a space, I like to have some coordinates on it, right, to understand it a bit better. If someone just hands you matrices, the natural coordinates are the matrix entries, right? But here, I'm not just caring about matrices, I'm caring about matrices up to row operations. Row operations change the entries a ton, so that's not a good choice of coordinates. The good choice of coordinates are instead the determinants of the maximal square submatrices, which are called the maximal minors. Okay, so we have some natural coordinates, which are called Plücker coordinates, right? And they're just what I said, these kind of maximal minors. So to describe one, I need to pick some subset of the columns, so some subset of 1 through n, and it should have size k. Okay, and the Plücker coordinate I'm going to denote by delta I of v. This is just the maximal minor of this matrix located in column set I. Okay, so for this point over here, if I wanted to take, say, delta 1, 2 of v, I'm taking the determinant of the submatrix in the first two columns. Sorry, I'm running out of space. And I see that that's 0. Okay, so this particular Plücker coordinate is 0. If I instead chose the Plücker coordinate delta 1, 3, then I would be looking at these two columns, and that Plücker coordinate is equal to 1. Okay, and these are the correct coordinates because if I do some row operations, all I'll do is I'll simultaneously rescale all Plücker coordinates by one number. Okay? Okay, so the other thing I should tell you about these coordinates is, well, they're more, they're obviously just looking at them, they feel more complicated than the matrix entries. They also have kind of another disadvantage, which is that they're not independent coordinates. So the Plücker coordinates satisfy a lot of relations and those relations, it's sort of even worse than they satisfy relations, they satisfy polynomial relations, nonlinear ones. So they're, yeah. So an example of such a relation is delta 1, 3, delta 2, 4 equals delta 1, 2, delta 3, 4 plus delta 1, 4, delta 2, 3. Okay, so you've got loads and loads of quadratic relations satisfied by these Plücker coordinates. And what that means is that the Grassmannian is a relatively low dimensional subset of its ambient space. Okay, so there are n choose k Plücker coordinates, right? As many Plücker coordinates as there are k element subsets of 1 through n. So yeah, so the Grassmannian GRKN lives in the projective space of dimension n choose k minus 1, but its actual dimension is k times n minus k. Okay, which is a much, much smaller number than n choose k minus 1. Yeah. Sorry, say again, this matrix? Yes, that's correct. That's correct. Yes. That's right. So these are projective coordinates. We sort of only care about them up to simultaneous rescaling. Yeah, that's exactly right. Yes. So you, so yeah, that's right. So, well, you could, right, so you could see GR1, okay, you can always get a one-dimensional subspace sitting inside of your two-dimensional subspace, right, by just kind of ignoring one of the rows. Yeah, but there's no sort of canonical way to see that embedding. Yeah. Other questions? Yeah. Yeah, I mean, I guess you're asking, like, so what you can do, what you can think about with these Pluker coordinates is you can kind of ask for like the volume of the parallelepiped spanned by those two vectors. And yeah, in this situation, those are parallel vectors, so the volume of the parallelepiped is 0. I don't know if that answers your question or not. Okay, maybe you can ask me afterwards if I don't understand. Okay, any other questions about the Grassmannian? Okay, forging ahead. So we don't care about the entire Grassmannian in this story. We care about a distinguished subset called the totally non-negative Grassmannian. I should say this definition is due to Postnikov and separately to Lustig. Okay, and the, oops. So the totally non-negative Grassmannian, which I'll usually abbreviate as TNN, is, well, all of those points in the Grassmannian, so all of those subspaces whose Pluker coordinates are non-negative, right? So I'm just sort of taking, I'm kind of taking the positive orthant in my big ambient space, right? And then I'm asking like which part of the Grassmannian sits inside of that positive orthant. Okay, and this is a full dimensional subset, so it is also k times n minus k dimensional. Okay, yeah. So I guess one question is, can you think of any better ones? I think my answer is I can't. Yeah, so you want something that's invariant under row operations. And so you sort of need some coordinates that involve all of the rows at once. And then you start thinking, yeah, like what sort of things involve, you know, all rows of a matrix and are invariant under row operations, and you sort of settle on, well, it should be something like the determinant. Yeah. I guess, oh, sorry, does someone else have, yeah. Yes. Yeah, so I guess, right, maybe I should say something where you can also do something where, so you can also do things like, okay, maybe I want to take a subset of the Pluker coordinates that are algebraically independent, so don't satisfy any relation, so I want exactly k times n minus k of them. And you can use those to express like all the other Pluker coordinates, but the formulas are very complicated. So this sort of has the advantage, like, yeah, you have too many formulas, sorry, you have too many coordinates, but they're all sort of relatively straightforward just looking at this matrix. If I chose like the correct number, k times n minus k, then the formulas get really complicated. Yeah. No, there are some restrictions, but I can tell you easily what sets are okay. Yeah. Okay, so yeah, Grassmannian, we've got these Pluker coordinates, and then we look at this distinguished subset, which is sort of like the positive orthant intersected with this very low dimensional space. Okay, and I think I'm gonna, yeah, mathematicians would scold me because you're supposed to like erase all the way over there, but that's really far away. So let me erase my motivation and draw you a picture of the totally non-negative Grassmannian in very small dimension. Okay, so Here is the totally non-negative Grassmannian for GR13. So this is lines in R3. Okay, so not so bad. And what this looks like, okay, so, right, since we're dealing with lines in R3, my matrices are just a single row, right, with 3 coordinates. And what the totally non-negative, yeah, actually, so, okay. So, yeah, let me, GR13, so if I have some element in here, it looks like the row span of just a single row, x, y, and z. And the Plücker coordinates here, those are the maximal minors, but I've just got one row. So actually here, the Plücker coordinates really are the matrix entries. Okay, so this is sort of the simplest case possible. Okay, and what I'm doing for the totally non-negative Grassmannian is I'm just asking that each of these entries is non-negative. Okay, and the picture is not too complicated. It looks like this. The inside here looks like kind of x, y, z, where none of those are 0. All of them are positive. And then, yeah, say this edge, maybe they'll do the bottom edge because that's easier. Like the bottom edge maybe looks like matrices where the first Plücker coordinate is 0, and then the other 2 are positive. Right, okay, and then this edge maybe is like this. And this one is like that. And then these vertices here are where all but one of the Plücker coordinates is 0, and that remaining one is positive. So this one had better be 0, 0, z, and this one is x, 0, 0, and this one is 0, y, 0. Okay, so that's the totally non-negative Grassmannian, right? And I said that it sits inside of GR13, which is just lines in R3, which is also the projective plane, p squared. Okay, so not too bad, right? In this example, I can draw it. I basically just get a triangle. Okay, and yeah, I guess I should say what happens. Okay, so maybe I'll keep k equals 1. I move up it to, but I increase n, so I move up to GR14. And this, okay, I'll test my skills. So this looks like a tetrahedron, right? A simplex of 1 higher dimension sitting inside of GR14. Yeah, so. Looks something like that. And I can kind of label the faces in a very similar ways to here. Okay, but I want to emphasize these are exceptions. This is kind of a k equals 1 phenomenon that we get something that looks linear like this. In general, you get something curvy. And I can't draw it, but these are the ones that I can draw. Okay, so you might notice kind of from, oh yeah, go ahead. That's right. Oh, okay, so there's some sort of duality, right? So k equals 1 and k equals n minus 1 are kind of the same. Okay, so those ones, but yeah, all the other ranges will be curvy. Right, the other thing to say is like in this situation, you don't have any of these complicated relations because these are, you need at least 2 indices of your Plücker coordinates to have these relations. Okay, so, gosh, this is the longest board I've ever seen in my life. Okay, maybe I'll move those up. Yeah, so you can see from that example over there that the totally non-negative Grassmannian is a space which breaks up very naturally into pieces. Right, so I had kind of the interior of my triangle, that's where all Plücker coordinates were positive, and then I could say, oh, this Plücker coordinate is 0 and the rest are positive, that brings me to an edge, like that. And that is not special to the linear situation, you can do that always. So the totally non-negative Grassmannian breaks up into pieces according to which Plücker coordinates are positive and which Plücker coordinates are 0. And I should say these pieces are called positroid cells. Okay, positroid is a portmanteau of two words, positive and matroid. I'm happy to tell you about matroids another time. The cell here is really important. This is this is a technical mathematical term. It means that all of the pieces actually just look like open balls. So they're not complicated. They don't have holes in them. They're kind of like the simplest possible pieces you could imagine. And this is actually a really big surprise because, basically semi-algebraic sets, so things cut out by like some things being non-negative and other things being zero, those are really badly behaved usually. They usually have lots of holes, complicated topology, but in this circumstance, all of our pieces are just going to be these very nice open balls. So I'll just write GRKN. It looks like the disjoint union of a bunch of these positroid cells S. And each one of these is an open ball. And even better than that, Galashan, Karp, and Lamb say that the way that I'm gluing together, like the way that these open balls all fit together, is basically like a polytope. So it's not linear, but nothing too complicated is happening. These pieces fit together. Like in a polytope. And this is there's a very precise mathematical statement here, but maybe I'll just leave it like this. Yes. Mm-hmm. Yeah, that's right. So so one thing that could happen, for example, is, one thing that could happen is in this big region, you could have a hole. So that could totally happen, but it doesn't. Yeah, and then what's happening is like these edges of the triangle are just gluing really nicely onto the open part. You're not doing any twisting. You're not doing any there's no coincidence here. Yeah, so you don't have to do something where you're like gluing different parts of the edge together, anything like that. You just kind of plop it right on. And that holds in general, even though the kind of edges, the facets or whatever won't be linear. Yeah, so really nice, totally, mathematically just very beautiful. Okay, so just to say, so I said we break up into pieces, these positroid cells, right? So here, the positroid cells are the open triangle where all Pluker coordinates are positive, and then this edge by itself is a positroid cell where I declare this Pluker coordinate is 0 and the rest are positive, etc. Okay, and maybe I'll do I'll even say a little bit more of an example. So yes, that's right. So there's one top dimensional one, and then lots and lots of lower dimensional ones all the way down to dimension 0. Yeah, okay, so just to give an example, so here is a positroid cell in GR26, so I can take all of the points in TNN GR26 where delta 1, 2 equals 0, and so does delta 4, 5, and all other delta ij are positive. Okay, so that's a perfectly good description of a positroid cell. And our example over there, our V over there, was an element in here. So I'm not going to write down the same matrix, but okay. So far I've only told you all the stuff that's really nice that happens. There's a little bit of a complication, which is or so far what I haven't told you really is how do you get your hands on how do you get your hands on one of these positroid cells, right? You can very well say oh yeah, I'm taking all of those subspaces where these two Pluker coordinates are vanishing and these ones are positive, but I mean, you don't really know anything about the cell when you say a description like that. So what we would like is a concrete way to actually produce every single subspace that lives in this cell. And that's where these graphs come in. Okay, so so the question now is, so we fix some positroid cell S. How do we obtain, describe, whatever you want? Maybe how do we how do we obtain concretely the subspaces in S? Okay, and Postnikov tells us that you can actually obtain all of the points in a positroid cell from a graph that looks like this. Okay, so I'm going to go into some detail about how this works to kind of reassure you that this is a very concrete procedure. Sorry if it gets a little too detailed, so it goes. So what you do is you're going to start with one of these on-shell diagrams or one of these Plabic graphs. And I'm going to run a procedure called boundary measurement to obtain all of the points in some positroid cell, which I'll call SG. Okay, so let me, yeah, I think I'll have enough space. Okay, so here's how it works. I'm just going to do this by example. So I'm going to start with one of my graphs. It doesn't need, in this situation, to be a graph coming from this recursion. It's just sort of any graph you draw in a disk like this with hollow and filled vertices. So here's such an example. Okay, here's my graph. So the first thing I'm going to do is I'm going to put some edge weights on here. So you should think about these as being positive real numbers that I've sort of picked in advance. And they decorate each edge. Okay, here are my edge weights. Okay, so the first thing that I do for this boundary measurement map is I'm going to orient my, right, so, okay, the point is we start with a graph and I need to produce loads and loads of matrices, right, or loads and loads of subspaces. So to do that, first I'm just going to put edge weights, these positive real numbers on all edges. And then I'm going to orient my graph in a very special way. So I'm going to orient it so that any hollow vertex has a unique ingoing edge, and the filled vertices have unique outgoing edges. And there are lots of choices for this, so I'll just pick one of them. Oh, and sorry, I should have labeled my boundary legs. Okay. Unique. Sorry, a little bit of math notation. Mathematicians are very excited about uniqueness, apparently. Okay, so I'm not, sorry, I should probably be going through it, but okay, I think I should have done it. So here's the unique ingoing for this hollow vertex, and then here's the unique outgoing for this solid, and etc. Okay, then, right, okay, sorry, I did this out of order. So this, I've already done this. I assign edge weights to each edge. Okay, and now I'm going to use this to produce a matrix. Okay, so I'm going to use this to produce a matrix, which I'm going to call the path matrix. I'm going to denote it by mg. And secretly, it depends on the edge weights, but I'm going to omit that for now. Okay, so this matrix, its rows are going that have an arrow pointing out of them, the boundary vertices with arrow pointing out. So here, 1 has an arrow pointing out of it, and 3 has an arrow pointing out of it, and all of the other ones have arrows pointing in. Okay, so 1 and 3 are going to index the rows of my matrix, and then the columns will just be indexed by 1 through n. So okay, and now the entries of this matrix are just going to record, okay, so I have this entry 1, 1, this is going to record the paths in my graph that go from 1 to 1. Okay, there's only one path. It doesn't do anything. It just stays. It's lazy. And so, okay, I'll record the weight of that path is going to be 1. Let me do another example so the weight is clearer. Okay, what about from this entry 1, 2? So this is supposed to record paths that go in my matrix, sorry, in my graph from 1 to 2. There's exactly one of them, and it travels along edges weighted A and B. So that means that the weight of that path is A times B, and that will be the entry that I put in my matrix there. So I always have to follow the orientation of the edges. So if I go down here, I can't get back up to 2 because this edge is also oriented down. Yeah. But there are examples where I have more than one path, and that's totally fine. So it's for this entry, 1, 6. So for that entry, oh, this might be kind of hard to see. Okay, so I can go from 1 to 6 either like that or like that. Okay, so now I have 2 paths, and so the entry that I put there is just going to be the sum of the weights of the 2 paths. Okay, so my first one is weight ACK, and then the second one is weight ADFJK. Okay, so I don't know if I've really given myself enough space to do this, but I will write it. Okay, so ACK plus ADFJK. Okay, and then there's also a sign sometimes, which is very predictable, which I'm not going to tell you about, but yeah. So there's also some sign going on, and for that particular entry, it needs to be negative. Okay, let me just do a few more. Here, the 3, 1 entry would be paths from 3 to 1. There is no way to get from 3 to 1 in this graph, so I have no paths, and that's weight 0. Okay, and same thing for 3 to 2. But then 3 to 3, there's kind of that lazy path of weight 1. Okay, this entry is 0. And then, okay, maybe I'll just fill in the rest of this matrix quickly. So from 4, there's one path. It has weight, I'm sorry, from 1 to 4, it has weight ADFH. And it gets a minus sign for reasons that I won't explain. From 3 to 4, there's one path of weight EFH. And then for 5, we have negative ADFI. And EFI here, and then EFJK here. Okay, so if you follow these rules, that's how the rest of the entries fill out. And it's a fact that this matrix actually has non-negative Kluger coordinates. I mean, it's kind of a surprise. I just cooked it up in this funny way. I decorated some signs, but yeah, so it has non-negative Kluger coordinates. So this matrix actually it gives you a point in the totally non-negative Grassmannian. And as I vary my edge weights over all positive real numbers, I don't change if Kluger coordinates are 0 or non-zero, right? I just change their value. So I stay inside of one positroid cell. And in fact, I sweep out the entire positroid cell as I change my edge weights over all positive real numbers. Okay, so yeah, so those were the boundary vertices that had arrows kind of pointing out from them. And there were only 2 of them, and those had to be my row labels. Yeah. Incidentally, that tells me that this is a K equals 2 graph, a helicity 2 graph. Okay, so right. Before I write down, I just said a lot of stuff. Before I write it down, I'm going to say one thing, which is that there are actually too many parameters here. So there are some gauge transformations that I can do without changing this matrix. And so I'm actually allowed to set some of these parameters equal to 1. I'm just going to erase them. So sorry, let me make sure I do it right. So I want to erase this one, this one, this one, and this one. Okay, so I'm allowed to set some of the edge weights to 1. And in the end, the number of edge weights I'm left with is the number of faces minus 1. Okay, and that's sort of the smallest number that you're allowed. Okay, so let me say this. So there's a gauge transformation of edge weights that doesn't change. Yeah, that fixes this mg. And so what this means is that you only need number of faces minus 1 edge weights here. Okay, if you have more edge weights that are just redundant, we can kind of bring it down. Yeah. Yes, that's right. Oh, yeah. Thank you. Yeah, so 1, 2 is 0, and then also 4, 5 is 0, because these columns are parallel. How many? Kind of. So you can tell which ones are 0 because they'll sort of, yeah, there is a way to read it right off the graph. The actual enumeration is going to be complicated, but given the graph, you can predict exactly which Pluker coordinates will be 0 over there. That's right. Yeah, so there's actually a way you can give me some combinatorial data about this matrix, and then I can build a graph for you that will kind of hand me that matrix. Yeah. Yeah, go ahead. A face. It's one of these kind of regions. Yeah, this is a face. That's a face. We have 6 faces. Oh my gosh, 7 faces. 1, 2, 3, 7 faces here. Okay, yeah. So I should need 6 parameters, which I think is what I have. Yeah. Okay. So we start with this graph. We produce this matrix. There's a little bit of fussing about exactly how many edge weights you need. But once you do this, you get what I've told you is I can start from positive real numbers to the number of faces minus 1. So I should think of these as being my edge weights. And what I told you is that this path matrix gives me a way to take my edge weights and turn it into a matrix, mg, which lives inside of a particular positroid cell. And the other thing I told you was actually, as I vary my edge weights over all positive real numbers, I cover the entirety of this cell. So I'm really hitting everything, and I'm hitting everything exactly 1 time. Okay. Yeah, so this, okay, so mathematicians would call this an isomorphism or a homeomorphism. Fine, it just tells you that for any choice of edge weights, I have exactly 1 point in here, and I've covered everything. This map is called the boundary measurement map. Okay, and so this means that I have basically an entirely concrete way to think about every point in this positroid cell. Okay, there are 2, yeah. It's just whatever positroid cell this matrix mg lands in. Okay, yeah, so it's some positroid cell. Okay, and then one more thing I want to say is it's not quite as nice as one graph gives me 1 positroid cell. There's some moves I can perform on this graph that don't change the positroid cell I get. Okay, so it's sort of like, yeah, it's sort of graphs up to moves give you positroid cells. And yeah, it's so far. Let me just draw the moves really quickly. They're not going to be that important, but I just feel like it's important to say. Okay, so this is moves on the graph G that don't change the cell SG. So I can sort of, I can collapse edges as long as the 2 vertices here are the same color. Okay, so I can do kind of an edge contraction. I can also take any degree 2 vertex and just sort of turn it into an edge. So degree 2 vertices don't matter at all. And then the last one is the square move. So if I have a local picture that looks like this, I can change it. So this is a square with alternating colored vertices. And I can change it to the other coloring of the square. Okay, so yeah. Okay, that's positroid cells. They come from graphs in this very explicit way. You can always, yeah, any positroid cell you want, I can come up with a graph that gives you it. Seems good, right? Because we started with some graphs over there, and we asked, can we find a geometric space that sort of has pieces indexed by these graphs, and then we want them to all kind of, different BCFW formulas to get different decompositions. Okay, so let's see how close, oh yeah, go ahead. No, I don't think so. Not the path algebra. Yeah, so I can tell you, right, so entries of this matrix corresponded to paths. It turns out that Plücker coordinates correspond to collections of paths that don't cross, that don't touch each other. And so you can just show, yeah, like given this matrix, it's sort of a classical lemma in combinatorics, the Gessel-Lindstrom-Viennot lemma. You can, given a matrix like this, you can model its Plücker coordinates, you can write its Plücker coordinates exactly in terms of some collections of paths. So we're going to go maybe from 1, 3 to 5, 6, and those paths can't touch each other. But yeah, if you just like take the weights of all of those path collections, that will give you exactly the Plücker coordinates. That's right. So you track really carefully cancellation and signs in that multiplication. Yeah, and it turns out to give this very nice combinatorial answer. Yeah. So that is definitely the physics perspective on these, is that, yeah, like I can't remember, maybe white is supposed to be like GR13 and black is supposed to be GR23. Yeah, I could sort of expand this using the moves into having only trivalent. Yeah, in math, not really. It's just like, these are the objects that we start with, these bicolored graphs, and what we can produce from them are these positroid cells. Yeah. Ah, very good. So basically, reduced, yeah, so as you do these moves to your graph, you could get something that looks like this with any coloring of the vertices. If you get something that looks like that, this is sort of a bad thing and it's not reduced. So reduced means I can do as many moves as I want and I'll never get a bubble like this. And there's some other things like if I allow non-reduced graphs, then, right, so reduced Playbit graphs that give you one positroid cell, they all have the same number of faces. But if I allow for non-reduced graphs, then those will have like more faces. They'll still give me the same cell. So it's definitely like not an efficient way to get the positroid cell. So that's why we throw them away. Yeah. It's sort of a technical condition. Okay. Any other questions? All right. So let's evaluate how well we're doing. We started with these graphs. We had a dream of a specific geometric object associated to those graphs. Now we have a geometric object associated to each graph. Is it the one we're looking for? Okay, so the summary of that was SG is a geometric space associated to the graph G. Is it the right one? For the purposes of connecting to BCFW formulas. Okay, and the answer is definitely not the right one. So what's going wrong? So the first thing is that all of my different positroid cells, SG, are disjoint. So we had this idea like each BCFW formula should give you a decomposition of one big object. But what's happening here is we've got some humongous object, this totally non-negative Grassmannian, and each BCFW formula gives you like some positroid cells, like one BCFW formula gives you positroid cells living over here, and then a different one gives you positroid cells living over here. So they just like don't talk to each other at all. So that's kind of not really what we were aiming for. Another thing that's sort of an issue is that the graphs that you get from the BCFW formulas always have 4K faces. Okay, so they don't have that many faces, right? So what this means is that SG is, oh, I'm sorry, they have 4K plus 1 faces. So the cell SG is 4K dimensional. And, well, 4K is a lot smaller than the total dimension of the Grassmannian, which was K times n minus K, right? So for most parameter values, 4K is going to be pretty small. So right now, the BCFW graphs, they're not telling us about full dimensional pieces or anything. They're telling us about very, very, very low dimensional pieces in the boundary, which is also not really what we wanted based on our goal. Okay, and then the last thing that I'll say is that there is a natural form that you can associate to each positroid cell. So the form of my positroid SG, oh, okay, and this form, it comes from the fact that each positroid cell is really just positive real numbers to some power, right? And we kind of have, there's a really natural d-log form over here, which is just the d-log form of the coordinates of this, yeah, positive r to some power. So, yeah, so I can write down a d-log form for SG, which is going to be the wedge over all of the edge weights. Yeah, so that d-log form, so dxc over xe. Or yeah, maybe I'll just write it as d-log. Okay, so this is a perfectly good form. It's sort of straightforward once you know that my cell is really just kind of like a copy of positive r. You can rewrite it instead of an edge weights in terms of Plücker coordinates, but it doesn't really seem like it has anything to do with amplitudes. So it can be written in Plückers. Not an obvious connection to the BCFW, yeah, no obvious connection to the BCFW terms. Okay, so that's where we stand. We started with graphs, we wanted geometric objects associated to them, we got some, but they're not the right ones. So what do? The basic idea here, I mean, I actually don't really know how Yara and Nima thought about it, but kind of like looking at this list, one thing that you might imagine doing is like kind of focusing on this part. We really want 4K dimensional spaces to be associated to our graphs. And instead we've got a much bigger space, so maybe we should squish it somehow. Maybe we should do some kind of projection and kind of hope that what we get in the end is 4K dimensional. And that seems good from this perspective too, because if you have something upstairs, you have like pieces of the boundary that are really far away. When you project, they can land on top of each other. So that also maybe will deal with this disjointness issue. Okay, so that's the idea of the amplituhedron. We're going to start with GRK, totally non-negative GRKN. This is too big, and we're going to squish it. And I think I have enough time maybe to say actually the definition of the amplituhedron. Oh, actually, before I go on, there's no obvious connection in this story yet to BCFW, but there are certainly connections to physics and on-shell diagrams. So there's a very nice paper. It has 6 authors. I think actually maybe even it's a book. So the archive number is this, 1212-5605. So the authors of this paper are Arkani-Hamed, Vojeli, Kachazo, Pasnikov, Trnka. I feel like I forgot Goncharov. Okay. Okay, and this book paper talks a lot about the relationship between these concepts and on-shell diagrams and other parts of physics. They don't talk about relation to BCFW because it's not quite there yet. Okay. So that said, I'm about to just define the amplituhedron and then I think I'll stop. Oh yeah, go ahead. Mm-hmm. 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 Yeah, so there are definitely certain coordinate transformations that we know that they stay the same, and they're coordinate transformations that have to do with these moves. If you just do something arbitrary, I am not that sure. Mhm. So I think like there are loads of different parameterizations coming from graphs. Like for example, I could have switched, like I could have changed the orientation that I started with. Definitely all of those forms will be the same. I mean, I think all of the forms should be like identifiable. Yeah, maybe I'll leave it at that. Yeah. So this particular case, I'm just talking about the graphs that come from the BCFW formulas. So those are special among the class of all graphs because I can build them up in exactly this sort of recursive way. And if you use exactly this sort of recursion to build up a graph, you'll always get a cell that's 4K dimensional. So this kind of graph doesn't show up in this recursion, for example. Oh yeah, please.
Given some n and k, even if k was, I guess, 0, or maybe not 0, maybe it was 1.
0 is boring, yeah, 1's fine.
Even if it was 0, you could probably use some complicated way to build it up in terms by doing BCFW. I guess here you think your k equals 0 is your building blocks.
That's right.
But I could think of it as...
Yeah, so, right, there's this thing where this BCFW bridge can be used to build up arbitrary graphs. This particular formulation, like the momentum twister formulation, really just gives you like a very special class of graphs that are relatively low dimensional. Okay, so now, having told us why these positoroid cells, they're nice, but not the spaces we're looking for, let me define the space we're looking for. And I think I will have to stop after that, and so that's where I'll pick up. I'll do it all the way over here. Okay, so the Amplituhedron. Okay. Okay, so to define the Amplituhedron, this is going to be the squished Grassmannian. What I'm going to do, so I'm going to fix my k and n. I'm also going to fix an additional parameter m, which is always 4 in the physics situations. And I'm also going to fix a matrix Z, which has, okay, so it's going to be n by k plus m dimensional, and it's going to have positive maximal minors. Okay, and the way that I've chosen my parameters, okay, I should say k plus m should be less than or equal to n. So this matrix here is going to be kind of a tall, skinny matrix. Okay, so this is n, and this is k plus m. Okay, and I'm going to use this matrix to define basically the way I'm going to squish the totally non-negative Grassmannian. So the Amplituhedron map, I'm going to write this as z tilde. So it's going to take me from totally non-negative GRKN, and it's going to send me into a different Grassmannian, GRK k plus m. And all that it's going to do, so I'm going to take my subspace V, or my matrix, my k by n matrix V, and I'm just going to map it to V times Z. I'm just going to do matrix multiplication. Okay, and that's the explanation for this, these indices, is that this matrix will be k by k plus m because of how matrix multiplication works. You might be a little worried, like, remember, to be a point in the Grassmannian, I need this, this matrix to be full rank. But that's guaranteed by the various positivity constraints that I have going on. So my V had positive Pluger coordinates, and then Z also has positive maximal minors. That tells me this is full rank. Okay, and then the Amplituhedron is just the image of the totally non-negative Grassmannian under this map. So I'm going to denote it by A and K MZ, and it's just, I applied the Z tilde map, this matrix multiplication map, to the entire totally non-negative Grassmannian. Okay, and I heard my timer ring, so I'm just going to say one thing about this, which is that this space over here was dimension K times n minus K, and this space over here is dimension K times m. And so because of the constraint that I had on K, m, and n, this will be a smaller dimensional space. So I really am squishing, or sorry, at one kind of, there's one parameter value for which these two things are the same dimension, but then otherwise this is a smaller dimensional space. So I really am doing kind of some kind of projection. Okay, and next time the place I'll pick up is I'll give some examples of Amplituhedra and then talk about how to mathematically formulate the problem we started with. All right, thanks so much for listening.
Thanks so much, Melissa, for this very clear talk. Do we have more questions? Yes, and please, if the people could use a microphone. Start.
Relations that you written, is that related to Schouten identities in
I'm sorry,
spinalicity?
you said Pluger coordinates?
Yeah, the relation that you written, 1, 3, 2.
Yeah, the quadratic relation.
Yeah. Is that related to Schouten identities we see in spinalicity? Or is it exactly the same? Or?
Okay, I see Suvrat shaking his head.
Sorry, I'm not an expert.
Okay.
The answer would be no.
Yeah, I'm not an expert either, so yeah, and Shruti says,
Sorry, can I just comment on that? Which is, if you look at the matrix that's constructed by putting all the spinors together, then the Plucker relations of that particular matrix will be exactly the Schouten relations between spinor helicity variables. So in that special case, yes.
I think we have another question or comment over here.
I just want to add to what Shruti said. So Schouten identity is like just the spinor helicity one is like a subcase of larger class of Schouten identities, where you have like a Levi-Civita of like rank D, and then you antisymmetrize D+1 indices by putting another tensor with it. And the Plucker relations come from that. If you write the determinant in terms of Levi-Civita, it comes from such an antisymmetrization.
Comments or questions? Maybe it's anticipating a little bit, but so you just define the map. So for the positive Grassmannian there on the right-hand side, what if I plug in there just one of these cells? You seem to like these positoid cells very much. What does that tell us on the left-hand side?
so yeah, the answer is in general maybe a little bit tricky. Yeah, but I guess maybe like to answer your question in the spirit in which it's asked, as soon as a mathematician sees a setup like this, where you have some space that you have decomposed in a very nice way, and then you're projecting it somewhere else, you ask things like, can I decompose the image in a way that's inherited from kind of the parent up here, right? So can I take some specific pieces up here and use them to cover the image? And this is sort of, yeah, mathematicians really like this, right? Because it feels like, you're just inheriting some decomposition from upstairs. And it turns out that, yeah, the physics situation, or kind of the thing that relates back to physics is exactly this sort of situation, where we're going to try to take, in particular, some like cells corresponding to BCFW formulas, and we're going to ask, do they cover everything downstairs? That's what we'll talk about in sort of more mathematical language next time.
Okay, I don't see any immediate questions, so let's thank Ms. again.